Okay, hello everyone, and thank you very much for joining the 101 stream today. This session is Parallel Sysplex Basics with Steve Warren from IBM. Before I hand over to Steve, I just want to quickly mention that you can put your questions into the chat box, and Steve will be able to answer your questions throughout the session. With that, Steve, I will hand over to you.
Okay, guys, welcome. This topic is a pretty big one, and as a result, to make sure I fitted it in the allotted time, I did record myself. So that benefits you in a couple of ways. You can ask questions as I'm giving the presentation, and I'll try to answer them, typing them while you hear my recording. And at the end of the recording, I will go live again, and you can ask more questions if you want. Again, this is a very introductory topic, so whatever question you have about parallel Sysplex, even the very most basic, that's the purpose of the GSE 101, is to level set you on base technology. So there is no dumb question. So please ask any and all questions. And with that, I will play the video, and looking forward to talking to you throughout the session. Hi, welcome. Hopefully you're at the right place. We're going to be talking about parallel Sysplex basics today. Let me tell you a little bit about myself first. My name is Steve Warren. I work in IBM Poughkeepsie, New York, across the pond in the United States. And there I work as a IBM Z technology architect in the IBM Garage for Systems. And what we really do is focus on having clients embrace the latest technologies on ZOS. So we're going to be talking again about parallel Sysplex, and parallel Sysplex is really the foundation for a highly available and highly scalable application set that runs on the ZOS platform. So come and join us for this whirlwind tour all about parallel Sysplex. So let's get down to the real basics. What on earth is a Sysplex, and why is it a good thing? Some folks new to the ZOS environment may ask, what on earth is a Sysplex? And so I wrote this simple definition, and I'll just read it before we move on. A Sysplex is a group of coupled yet distinct clustered instances of ZOS images that cooperate to provide a virtual single ZOS instance view to applications with the goal for high availability and capacity by providing messaging between various images in the Sysplex and data sharing between all of the images. In 2021, companies need to have applications that are always available, 24/7 by 365. If there is an outage, and it's a planned outage because we need to apply maintenance, we still expect that application to be running while we apply maintenance to one part of our system. And when we have unplanned outages, when things are going bad and something goes down, we need to make sure that the system can recover from such of those events without disruption to our business workloads and to restore the original configuration as quickly as possible. Parallel Sysplex addresses both of these by having multiple images of ZOS that are working together in parallel to accomplish the goal of having the application always up. And there's a number of technologies we're going to be talking about that just focus on making sure that we're continuously available, regardless of a planned outage when we have to apply maintenance or do some other kind of configuration change, or whether we have some severe unplanned outage. Parallel Sysplex addresses the idea for having continuous availability for our applications. What's another reason why people use parallel Sysplex? Well, it's very simple: more capacity. Parallel Sysplex is a much more scalable solution as you increase the workload on your systems. There's something called a multiprocessor effect, which means that just because you add more processors to a problem and have more threads running doesn't necessarily mean that you get better performance. In fact, if you reach a point in this curve as shown in the blue line here, adding number of processors actually can have a detriment to your workload. Okay, it's known as the multiprocessor effect. And so it doesn't take a very large number of CPUs before a single system image will deliver less effective capacity than a Sysplex configured of 2 systems, each with half as many CPUs. Or, let's do it again, a Sysplex of 4 systems, each with a quarter of the CPUs, can do even better. And so you get near linear increase in the processing power when you use parallel Sysplex, as denoted by the dotted line. Of course, the perfect linear would be a 45-degree angle here, which is ideal, but parallel Sysplex comes pretty doggone close. And for the number of systems that we use for parallel Sysplex today, it delivers almost linear growth as you add more systems, more images to the parallel Sysplex. You can get as close to linear growth as you're going to get. As opposed to just adding more processing power for one image, you're not going to see that benefit. In fact, you might even see the performance go worse. So again, the two major tenets of Sysplex: availability and capacity. Let's learn about some basic terminology and concepts regarding a Sysplex and how those components are used to provide business value. Okay, here's a simple example of an application running on top of middleware being DB2, Kix, IMS, MQ, WebSphere, etc. Application environments that an application can run in, and of course that middleware runs on top of ZOS. So if we have just our application set up this way, we really have a single point of failure. And when we have this single point of failure, God forbid if the application, the middleware, the operating system, the hardware goes down, or even the data, we are in trouble and we have our application can become unavailable. So we might think of adding some redundancy to avoid this outage instead of having this single point of failure. And so we might consider a model that looks something like this, where we have an application that maybe can be replicated to run in 2 places at the same time. And so can we actually do that? Do we want to actually replicate the data so that we avoid a single point in failure for anything, whether it's the operating system, the middleware, etc. Now the middleware already today, all the middleware products that run on ZOS already do parallel Sysplex quite well. The issue is going to be, can your application also exploit parallel Sysplex? What's the recovery model if something goes down? How do you recover? Can these applications really have true Sysplex awareness in terms of being able to take over someone else's work, being able to go to another copy of the data? How do we detect when a failure actually takes place? What about network connections when we have a failure? What kind of serialization do we have in place so that if one or multiple copies of the application are running, we only have one copy of the data, we only have a single application that is actually processing an individual's request, and can this thing scale out? So all of these things, the application framework and the foundation for being able to have this multi-system application that can lead to high availability and scalability, that's what Parallel Sysplex provides, this foundation for dealing with these type of issues. But it doesn't come along for free, and all of these things require thought in order to be able to Sysplexify your application. Okay. So in Parallel Sysplex, we want to make our application highly available and scalable, as we just talked about, right? So we want multiple copies of an application running on multiple ZOS images or servers, again, to have higher availability. But all those applications instances need to share data. If the application needs to talk to each other to share the data, it won't be scalable. If I add one new server, each server would need to talk to that new server. What if we had a common repository with serialization built in, and the servers could just talk to the common repository? And what if the server could just find out if their in-memory version of the data is the very latest copy very easily? Well, this is kind of what the coupling facility is. It's an intermediary between the servers and the data. The server can make one simple call to the coupling facility to get serialization to make updates. So we can get that high speed access to the data with total coherence of that data. If we just need to talk to one place, the coupling facility. No need to talk to other servers. That is truly scalable, and that is one of the major benefits of parallel Sysplex. Okay, so here is just a high-level view of some of the major components that make up a Sysplex. So we usually think of a Sysplex between 1 and 32 images. Generally speaking, a Sysplex that most clients are going to understand is at least 2 or more systems that work together into a cluster. Now, these images could be on the same mainframe box or CPC, or they could be, for higher availability, hardware redundancy, to be on at least 2 or more CPCs or mainframe boxes. So, we want to have this Sysplex, and XCF is the component of the operating system that manages a number of things in something that we call a base Sysplex, which we'll talk about in just a moment. So XCF manages the communication between 2 or more systems in the Sysplex. That communication goes over something called signaling paths. XCF uses this thing called a coupled data set to manage configuration and state information related to the Sysplex. And you're going to need, of course, to have a common time reference so that you know which event in the Sysplex took place first and which one took place second, etc. There's another component called SES or XES, and that component is the component of the operating system that deals with the communication to the common storage of a Sysplex, which is called the coupling facility, and the various different types of structures that are available in that coupling facility. You're going to learn in just a moment that coupling facility is just another operating system that runs in another LPAR in a CPC. And so using the SES components, applications are allowed to write to this common shared storage for true shared data amongst the various members of the Sysplex. There are several different configurations of a Sysplex. I can have a single system Sysplex versus a multi-system Sysplex. A single system Sysplex is not really too useful and doesn't provide availability and scalability, but there are these modes that I can have the Sysplex in. XCF local mode, where there's no coupled data sets and no coupling facilities. We'll talk about that later, what those things are. A monoplex, which may have the same infrastructure as a multi-system Sysplex, except there's only one system allowed in that Sysplex. And finally, a multi-system Sysplex, which is what we think of and which has the characteristics that we're striving for with Sysplex. There are 2 Sysplex configurations, a base Sysplex and a parallel Sysplex. I'm going to tell you right now, it's a very simple distinction. If you have a coupling facility that's used for data sharing or resource sharing, you have a parallel Sysplex. If you do not have a coupling facility in your Sysplex, you are known as a base Sysplex. It's that simple. So here's a visualization of some possible base Sysplex configurations. In the upper left-hand corner, we have an example of 2 ZOS images that have joined a Sysplex that reside on the same CPC or mainframe box. They are connected. Remember, all systems in the Sysplex have to be connected to one another through something called a channel-to-channel connection. And that channel-to-channel connection, otherwise known as CTCs, will be able to allow for communication between those two systems. Now, if you go look just below, it looks remarkably similar, except in this case, System 1 and System 2 are on different mainframe boxes, but they're still connected through the CTC connection. So what added value is that? Well, of course, it provides greater availability in the case of a hardware failure, or in the case you need to swap out the hardware for a new version of the hardware, for example. You will not take an outage for your entire Sysplex because that other system is still up while the other one is being taken down, or it fails for some reason. On the right, of course, you can mix and match and have multiple systems in a Sysplex, some that reside on the same CPC and some that do not. So by doing so, again, you can improve availability by having more systems within the Sysplex, of which some of them are on different CPCs or mainframe boxes and others are on the same one. And again, remember, since there is no coupling facility in this methodology, the only way of communicating between these devices are to use what's referred to as these CTC connections. And remember, they're any to any. So Sys1 needs to talk to 2 and 3, Sys2 needs to talk to 1 and 3, and Sys3 needs to talk to 1 and 2. When we're talking about parallel Sysplex configurations, we have to take into account the placement of both the images that are in the Sysplex, in this case example Sys1 and Sys2, as well as the coupling facility placement. And in particular, we need to understand the placement of the CF images in relation to the systems in the Sysplex. And so in this upper left-hand corner, we're dealing with something which is called an external coupling facility or standalone coupling facility. What that means is that that particular CPC mainframe box only contains coupling facility image or images. Okay, so by doing so, you're failure isolating that particular coupling facility to a particular CPC. So for the most highly available configuration, this is a good technique. It is more expensive, though, to do a standalone coupling facility, as you have to have separate CPC boxes dedicated for coupling facilities. So in this example, we have basically 4 CPC boxes, one running System 1, one running System 2, one running CF1, one running CF2. On the bottom, we have the introduction of something called an ICF, an internal coupling facility. All that means is that the coupling facility is actually running in an LPAR that also is running other LPARs with other operating systems running. For example, our ZOS Sys1 LPAR. So in this case, we have Sys1 and ICF1 are co-located on the same hardware, while System 2 and Coupling Facility 2 are on separate CPCs. So again, we don't have failure isolation here between System 1 and ICF1. So God forbid that the CPC that contains Sys1 and ICF1 goes down, there's going to be more extensive recovery that may be necessary to be able to recover from that scenario. Because they're not failure isolated between them. So you're losing multiple entities in the Sysplex when one piece of hardware goes down. In the upper right-hand corner, we see the idea of, again, 4 different CPCs, but in this time, instead of having standalone coupling facilities, those coupling facilities reside on CPCs which contain other LPARs. But in terms of my 2 systems, System 1 and System 2, this is very much similar to the upper left-hand corner, because the coupling facilities are external to me. And so, again, this can provide a little more resilient configuration. and what you can failure isolate your coupling facilities from your LPARs in your Sysplex. And of course, you can do any combination here. So in this bottom right-hand corner, you also have a couple of systems here, and you have a couple of ICFs, and they're all interconnected. Some are on the same KEX, some are not. So again, depending on your configuration, is going to determine the recovery that's going to be required should one of those KEX go down, or when, for example, when we have to even bring them down for maintenance. So again, very important for failure recovery. All right, now let's talk about how we take our ZOS images and have them join and leave the Sysplex. It's quite simple. A system joins a Sysplex at IPL, and the system leaves the Sysplex at wait state, or when the system abnormally ends and cannot be easily restarted. Let's talk about joining. So when you join the Sysplex, you're going to be joining a particular Sysplex name. Does that Sysplex, do you have access to the same couple data set? Do you have the proper signal connectivity? Do you have the same time reference as all the other systems in the Sysplex? No update should ever require a simultaneous Sysplex-wide IPL. Usually what we do in Sysplex technology is we do what's called a rolling IPL. If we need to apply updates to all the members of the Sysplex, we can update them one at a time, and eventually all the systems in the Sysplex will have that update. Now, when a system wait states and is no longer available, the surviving systems have the responsibility to remove it from the Sysplex and to make sure that it has been appropriately isolated from those shared resources. And once that Sysplex partitioning has been completed, the survivors can then be notified and perform the appropriate cleanup for the system. We'll talk about that in just a moment. So let's talk a little bit about sympathy sickness. There can be a single system that you can refer to as in a sick but not dead condition. This is really when a single sick system holds resources that are needed by other systems within the Sysplex. And eventually that one sick system can cause those other healthy systems to experience a sickness-like activity because of that one real sick system. That's referred to as sympathy sickness. So, routing work away from that troubled system doesn't guarantee necessarily that the other systems will not be impacted. And when you allow this non-terminating problem to persist, it's not actually helping the problem, it's actually hurting the problem. And so what we want to do is, when a system becomes unresponsive, we want to remedy that and take that system out. The problem is we need to be doing this kind of balancing act between acting too soon, it would have eventually recovered on its own, or acting too late. These innocent parties, the other people experiencing this sympathy sickness, are suffering serious harm. And so operations sometimes it needs to intervene, but we try to automate this as much as possible through things like something called Sysplex Failure Manager, which tries to timely intervene to identify the culprit and to take corrective actions. So how does parallel Sysplex actually detect an unresponsive system? Well, this is a lot of information right here. I'm just going to sum it up in a very simple way. Periodically, a system is going to write to the coupled data set a time of day timestamp into the Sysplex to indicate the current status of that system. In addition, a time of day indicator is also sent whenever we send messages back and forth between the systems. So every few seconds, each system is going to read the time of day from each peer system, and it's going to be looking at also the time of day indicators over these signaling paths. And the key is that if both the signaling paths, time of day, as well as the status time of day exceed the failure detection interval, then we conclude that the subject system is unresponsive. And when it's unresponsive, we are going to take some action to remove that system. Well, what happens when that failure detection interval is exceeded and the system is declared to be unresponsive is that Sysplex partitioning comes into play. Sysplex partitioning is the act of removing a particular ZOS image out of the Sysplex. And so what's going to happen is there's a whole bunch of stuff that goes on here. One of the big things is that that system is failure isolated and that it can't be updating the shared data anymore. And then we can go ahead and then do cleanup on behalf of that other user and try to recover from whatever actions may have been taking place at the time. And then the system is officially no longer in the Sysplex. So the key point in this slide is that we really need to make sure that isolation of that failed system has been completed before we go ahead and do any other cleanup. So what do we mean by that? So if we don't isolate the system, we create the potential for data corruption. And so we certainly don't want to have multiple updates to this data. The manager of the data is trying to change a value inside of the shared storage or shared resources, and meanwhile this other system still has not completed its I/O, and so now it can overwrite or overlay data. And so XCF will not remove a system from the Sysplex until it has been isolated. There's a couple different ways that you can isolate. If you're using parallel Sysplex, you can use fencing. We can use something called System Status Detect Protocol, which uses a ZOS component called BCPII to actually talk to the hardware. And then we can also do it manually. If you're running in a parallel Sysplex, one technique that can be used is fencing, and basically a command is sent via the CF to the target KEK to fence a particular system instance. And basically this is in conjunction with the hardware, and the I/O activity is ceased. Another way of initiating Sysplex partitioning is to use something called System Status Detect Partitioning Protocol. And a system SSD uses BCPII, which allows parallel Sysplex to have kind of like HMC-like control over systems in the HMC network. And basically, XCF is going to reach out to that other CPC and say, is it dead? If it is dead, it can remove the system out of the Sysplex right away. So this is a cool protocol, because what this amounts to is a single missed heartbeat by XCF from one of the systems will cause XCF to reach out to BCPII and say, hey, is that system dead? If it is, it can remove it out of the system immediately. And so instead of waiting for the full failure detection interval that Sysplex Failure Manager normally requires before partitioning someone out of the Sysplex, instead we can partition him out instantaneously, because we've already determined through BCPI that that guy is dead already. And so again, removing the guy out of the Sysplex as fast as possible is going to allow the sympathy sickness that resides on these other systems to be as minimal as possible. Let's discuss some key points about couple data sets. There's a lot of things on this slide, but I just want to dumb it down to the very basics. A coupled data set provides a central data repository that is visible to every single system in the Sysplex. So that coupled data set and all the accesses to the data inside it are managed by XCF. XCF does not use any of the standard access methods to access it, but uses its own channel programs to actually access the data. And by doing so, you're able to store shared configuration and shared status values of various activities that are going on with all the Sysplex members. Because every system in the Sysplex needs access to the couple data set, this could represent a single point of failure. So that is why in a standard configuration, we always have a primary and an alternate couple data set. We need to be able to always access the status values, and we also need to be able to access configuration controls that are contained within the couple data sets. And so when we read from the primary couple data set, XCF, it's going to read from the primary couple data set. And when it updates, it's going to write to both the primary and then the alternate. And both have to complete. So a Sysplex can automatically switch to the alternate if the primary fails. And hopefully you have some automation in place to add a new alternate couple data set if either the primary or the alternate fails. You always want to have two, because if you lose both of them, in many cases you can actually wait state, and in some cases wait state the entire Sysplex. And so these data sets are very important. We want to make sure that they're highly available. And again, we have something called ZOS Health Checker, which can actually make sure that you have two data sets defined for your couple data sets. Now, there are multiple kinds of data sets. We've been focusing on the very left, the Sysplex couple data set, which is really going to, again, manage status and state information within it. And it's very critical for the Sysplex. But also there are other couple data sets. Sometimes we refer to them as functional or function couple data sets. If you want to ever have a parallel Sysplex, you're going to need to have something called a CFRM couple data set, which is the coupling facilities controls for your Sysplex, where all the structure and connector information is located. And you can have, in all of these that are listed here, you can have the idea of an active policy as well as other backup policies in case you need to switch to a different configuration. They're called administrative policies. You can also have something called Automatic Restart Manager. It has its own couple data set to be able to restart various system tasks or user tasks that are on the system. And you also have something called Sysplex Failure Manager, which we talked about before, which helps to maintain the Sysplex running optimally. And if one system is sick, we can partition that guy out of the Sysplex quickly. There are also other couple data sets. Workload Manager has its service definitions inside of a couple data set. Logger, which has common logs for all the systems in the Sysplex. You can have the idea of log streams and structured data, logging first writing to the coupling facility and then eventually getting written out to DASD as a fast write type of technology. And then even Unix System Services also has its own couple data set. There are other couple data sets as well that are used in the system, not just the Sysplex couple data set. All right, let's quickly talk about XCF services. Okay, as we said before, XCF is the gatekeeper to sort of determine which systems can get in and out of the Sysplex. It also, though, provides a series of APIs that various services can exploit within the Sysplex. So if you can imagine that you have a multi-system application, you can imagine that you have instances running on different systems within the Sysplex, right? And those instances might need to be aware of each other. They might need to communicate with each other, and they might want to monitor the status of each other. So you can think of each of the various instances of this multi-system application are members of an XCF group. So what's going to happen is the application is going to define a group and it's going to join as one of the members of that group. Other systems, when you start other application instances in this multi-system application, they are also going to join the same group. And by doing so, you have all the instances of your application are members inside of this one XCF group. And then once you're in this group, the collection of those application instances, I can now do certain things, such as sending messages to various members that are in the same group. And what's cool about this is that XCF, of course, doesn't require you to actually know where that other member resides. You just send a message to the member, and XCF will deliver that message. So these guys can be on multiple systems. You can even have XCF messages sent to a different address space on the same system. So again, this multi-system application is going to have members within this XCF group, and XCF provides services to allow those applications to interact and to monitor even the health of the various members in the group. As we mentioned before, every single system within the Sysplex has to be able to have signaling paths to every other system in the Sysplex, and so we're going to talk about that just now. This chart is incredibly complex, and just to show you that there is a lot of complexity involved when you are sending messages between one system and another system. So, in a nutshell, when you are sending a message, you need to have a set of buffers, a buffer pool of which these messages are going to be sent. And then you're going to have a buffer pool on the inbound side where that message is received before it's delivered to the recipient of that message. You also have to have particular signal paths that are defined between the various systems in your Sysplex. And so when we send a message, we have these set of pools of buffers that we can use to send messages across. Then that message pool is then going to select a particular path, a path out from my local system and a path into the other system. The other system is going to receive that message. It's going to be put in an inbound buffer pool and eventually delivered to the recipient of the message. So traditionally, we divided these resources in terms of something called transport classes, which allowed you to separate resources for certain types of messages. That being said, with ZOS 2.4, we've done something called transport class elimination or simplification. And for most type of messages, there's no longer need to specify transport classes, which is basically having a dedicated pools and paths for a particular message to be sent to another system. Instead, we allow the system to manage that, and that is no longer necessary. What we're trying to just say here is that there is this idea of buffer pools on both sides and specific paths of which that message is actually going to be sent across. There are two types of XCF signaling paths. There's a CTC signaling path and a CF list structure signaling path. So if you're in a parallel Sysplex, you of course can avail yourself of either one of these options. If you're in a basic Sysplex, you only have the option on the left. I would recommend that most folks consider using CF list structure signaling paths. This is much easier to set up, especially when your Sysplex is more complicated. And so remember, you have to have any-to-any connectivity. So Sys1 in this case has to have connections to Sys2 and Sys3 and vice versa. All the systems have to have any-to-any. When you have 3 systems, it's okay. When you add the 4th system, now you have to have any-to-any to 4, etc., etc. And so with the CF list structure signaling paths, I basically am going to define a structure within the coupling facility and then I can just have all those other systems connect to it. It's kind of like what they refer to as the mailbox approach, is that basically Sys1 delivers a message for Sys3, and then immediately is routed to Sys3. And so this is a much more simple arrangement. And it has, with today's coupling facilities, it is a very, very fast data transfer rate. And so recommended if you're using parallel Sysplex and coupling facility to use this right CF list structure signaling paths. All right, let's talk about a major component of a parallel Sysplex, the coupling facility. All right, so let's talk about how data sharing works between ZOS images by using the coupling facility. Okay, so on the left here, we have multiple ZOS systems that are nodes in the Sysplex. In this picture, they're on the same CPC or mainframe box, but of course they could be located anywhere. On the right, we have a coupling facility. This coupling facility here is pictured in a standalone box, but certainly could be an internal coupling facility running it in its own LPAR on the same CPC or a different CPC as these other ZOS images on the left-hand side are showing. This LPAR, the coupling facility, is running its own unique operating system called the CFCC, or the Coupling Facility Control Code. Releases of that coupling facility control code are commonly referred to as CF levels, and for each hardware release, there usually is a corresponding new CF level. Okay, so on those two ZOS images here on the left are multiple users of the coupling facility. To use the coupling facility, you must first need to invoke SES services, XES, in order to connect to it. So in this example, we have at least 3 applications that use the coupling facility. They're referenced here as connectors. These applications might be a single multi-system application that's spread across multiple ZOS images in the Sysplex for higher availability or scalability, or in this case, they could be slightly different applications. When these applications invoke SES will eventually send that request over these CF links that we have pictured in the middle that are between the ZOS image and the coupling facility, and they deliver that request to the coupling facility. So what happens after that? Well, the coupling facility is going to take that request and determine which structure does this request apply to. And note, in this example, we list the 3 distinct types of structures: a list structure, a lock structure, and a cache structure. The names are kind of self-explanatory all on their own, but let's have a simple introduction to what they do. Okay, so first, the list structure. The list structure can be used by an application when it needs to share information organized as entries on a set of lists or queues. This is common like when you have applications that want to, let's say, distribute work or maintain shared status information. A lock structure, on the other hand, can be used to serialize user-defined resources at any scope that that application requires. Basically, it's like a locking protocol that's shared amongst many systems. And lastly, a cache structure. A cache structure allows high-performance sharing of frequently referenced data as opposed to a much slower data access on disk. So typically the way caching works in this environment is that these connectors are going to keep an in-memory copy of the cache represented by the CF structure. So each one of the connectors is going to have in their memory an in-memory copy of that cache. Obviously, a local in-memory copy is the absolute fastest memory access. But of course, that cache could have been changed by one of the other connectors. So how on earth does a connector know that their data, their in-memory copy, is current or obsolete? Well, that connector can register interest in knowing when the cache has been updated. If they do that, then the coupling facility will automatically send a notification to the CPC where that connector resides. And how does it make that notification? Well, it updates a vector in the hardware on the local system, pictured in this picture called the local cache vector. Okay? This local cache vector is in an area called the hardware service area, or HSA. And it updates that again when an update is made that makes the in-memory copy of the cache obsolete. So the application, when it is looking at its in-memory cache, before it looks there, it's going to simply inquire via a very fast instruction to the hardware of whether or not their cache has been invalidated. If it's not, and my in-memory copy is still the most current, then I have my cache. I can just use that data. It's the most current stuff. If, on the other hand, it has been invalidated and has been updated by some other connector, we can still call a fast CF call to read in the more current version of that from the coupling facility and update our in-memory cache. So by doing this, you really have a high-performance data coherent solution. Now for list, it's going to work in a very similar mentality or method. If I, as a connector, register to be notified when a list transitions from empty to non-empty, in other words, whenever something makes the list go from a length of 0 to some other value other than 0, when some other connector adds something to the list, I can have, what that will cause is the local list vector on my CPC to be updated. And when that gets updated, my application can be woken up and have my user-defined routine receive control to process those items on the list. So that in essence, I have notification when I have other connectors making modifications to that list. So this is really what interaction with a coupling facility looks like. Connectors communicate through the SES components of ZOS to communicate to the CF, and if the user wishes, it can receive CF notifications through the hardware when certain activities initiated by other connectors take place. So on the previous chart, we talked about these CF links that are connecting my ZOS operating system with the actual coupling facility. And all this chart is trying to show for this presentation is that there are lots of hardware technologies, some of which are more current than others, and that can be used to connect between your ZOS image and the coupling facility. And so you're going to need to make sure that you're running the latest technologies in order to make that, that CF link connection possible. In a nutshell, what this slide is trying to convey is that requests to the coupling facility can either be synchronous or asynchronous. If my application can tolerate making a request to SES, waiting for the coupling facility to perform that action, come up with a response, send it back, all before I receive control again, then of course that might be cost efficient then to process the request asynchronously. But of course during that time period I can't do anything else. So asynchronous may be an opportunity if you have a request that the coupling facility might take a while to complete, that you might consider doing it asynchronous, be able to do additional work, not tie up the CPU during all that time, and then when this coupling facility is done, now I can be notified that it's completed and then pick up that work where I left off. Let's talk about how we recover shared data in a parallel Sysplex environment. There will be cases where I need to make a copy or to reconstruct the data in a CF data structure. CF structure rebuild can make all this happen. So for maintenance purposes, for example, I may want to make an actual physical copy of the data from CF1 to CF2. I'm bringing down CF1, I'm going to apply maintenance, and I need to copy the structure contents over to CF2. Structure rebuild can make that happen. Likewise, it can also happen when I need to reconstitute or reconstruct the data in the structure through, for example, hardened logs, so that I have the most current data in my coupling facility, which is the faster access by the system rather than going out to DASD. So as you can see, there are a number of reasons why I need to do a structure rebuild. So there's two basic types of rebuild, a simplex rebuild and duplex rebuild. So you can think of a rebuild is going to create a brand new structure, and when that new structure has been populated, we are now going to get rid of that old structure. So basically we're taking one copy of a structure, making a new copy, and throwing away the old. In the case of duplex rebuild, I actually am going to allocate a new structure. I'm going to populate the new structure, but now I have both the old and the new. And when I resume activity, I am now going to make updates to both copies of those structures at once. So there are advantages and disadvantages of both. The lower duplex rebuild has the capability of having a more easy recovery scheme. If one structure goes away, I still have the same copy of the data in the new structure, for example. That does come at a premium, though, because there's more overhead associated with writing multiple copies of the structure. As opposed to the simplex, of course, it's the opposite. It has faster performance because I only am writing to one copy, but it has a more difficult time of reconstituting that data in the structure should that structure fail. I need to take hardened data from logs to repopulate the structure. As we talked about earlier, failure isolation means that any one thing going down doesn't cause very complicated recovery. And so when we have these scenarios where we are envisioning a failure, and we have to take all these failures into consideration when we're designing our application. And so, for example, if one coupling facility goes down, how complicated is my recovery going to be, and what is my recovery going to be? What happens if I lose connectivity to any one of the coupling facilities from any other source? What am I going to do for recovery? What happens if the entire CPC goes down? What do I do for recovery? So, in the case of duplex structures, you're going to get fast, robust failure recovery. And so when you have a failure situation, it's going to take a lot less time. And so in this example over here, you can see that we have a couple of different solutions here for duplex structure recovery. So in the case of System 1, System 1 is writing its data to both external coupling facility 1 and external coupling facility 2. So if CF2 goes down, for example, I still get the data off of 1. If CF1 goes down, I can still get the data off of 2. If the KEK that contains Sys1 goes down, if I restart that system, I can still gain access to that data on another from another system. So the bottom line is I can structure my configuration such that I can minimize recovery. And so there's different duplexing options. There's something called system managed synchronous. There's system managed asynchronous for lock structures. And then there's something called user managed duplexing also. So again, on the BOM diagram, we also have another example of this, where in this case, System 1 writes its data to both a local coupling facility, internal coupling facility 1, and it also writes to internal coupling facility 2. So what that means is that we have a failure isolated system here. So if we lose one of the ICFs, we can easily recover. We have another place where the data is, and we don't have to have a complicated recovery from logs, usually reading from DASD and reconstituting the contents in the coupling facility. Let's talk about common time reference. The point being made here is that the common time reference is not just on a single mainframe CPC or KEK. It can span multiple CPCs that are in the same Sysplex. Okay, so this picture basically is just showing how the timer protocols really work. There's going to be one CPC that's going to be called the preferred time server. That CPC is responsible for distributing the time signals. And those time signals are going to cascade through this time network so that all times in the CPC will be in sync. Again, this is crucial for the ordering of activities in the Sysplex. The Sysplex acts as one big server, and their times need to reflect that they all are in coordination with one another. Critical for an effective Sysplex. Let's go back to the subject of high availability to wrap up our discussion today. So what this chart is trying to really demonstrate is that in an ideal, highly available framework, we really want mirror copies of your application sets and the underlying software to be in multiple places. What that means is that I can have the ultimate in high availability. So when a work comes into my Sysplex, it can flow into the coupling facility so that every system has access to it. One system can pick up that work, but if another system goes, if that one system goes down, another system can just go ahead and seamlessly pick up that work. Of course, maybe there are some in-flight transactions that need to have some recovery, but in general, I still have high availability. New work coming into the system can still be processed by the remaining systems that are all clones of each other. If you don't have clone systems, you might have to do what's called a failover, where one application is restarted on another system so that then that application can run over there. The problem is that during the time it takes for you to start that application, you have your application unavailable. So not desirable in that framework. Well, when we're talking about parallel Sysplex and high availability, we need to talk about service restoration models. And really what we want to aim for is this upper high availability model where basically there's no service disruption. So in other words, if you have a failure that takes place, what ends up happening is that I am able to have my other systems in the Sysplex pick up that work seamlessly and be able to handle that guy going down. Meanwhile, you can restore that guy and bring him back up to, again, have the same capacity as you originally had. If you can't do that model, you're going to have a service disruption time period where you figure out, maybe I have to do a failover and restore that workload over on another system. Maybe it can be automated to some extent where I start that workload up on the other system, but it's not instantaneous. There is a period where that application is unavailable. And then lastly, a highly manual process where something goes down, I have to manually figure out how I'm going to restore the service, and that could be measured in a very long amount of time before I have the service return to normal. Okay, so let's wrap things up. Well, I hope in this last hour you've learned some of these terminologies, and now that these terminologies don't seem quite as intimidating as they did before. I would encourage you to look at some documents such as setting up a Sysplex to gain more insights about some of the details surrounding these technologies. I'd like to thank you for joining me on this journey. Please, my email is on the title page. If you have any questions, please feel free to reach out to me. This session does go over a couple minutes, so I probably won't be able to take additional questions at this time, but I'd like to thank you, and please take a moment and fill out your session evaluation. You can scan the QR code or go to this website. Thanks a lot and have a great day. Hey everyone, I'm here. I do have a couple of minutes for questions. I think I trimmed a couple of slides out of the deck from what I originally had. So if you have any questions, I can try to take them at this time. We already had a number of questions that were in the chat, which is great. And so I'm very pleased that you guys had some questions. Any other things? It can be the most basic question. There were some pretty highbrow questions that were asked in the chat for Sysplex 101. Very impressive, but you can ask the most basic question if you'd like, and I'll be here to answer it. So with the absence of additional questions, I guess we can say that this session is a wrap. Lena, thanks for inviting me to present in the 101 track. And you can always feel free to reach out to my email, swarren@us.ibm.com. And I'll be happy to answer your question offline as well.
Thank you so much for the session, Steve. I will close the Zoom now. Thank you very much. Bye.
Thank you, guys.